All right, so we're beginning for section 2. I thought I had uploaded this video, but apparently it didn't go through. So we'll give it another go. All right, section 2 is all about the properties of your different waves. So we're going to talk about your mechanical and your electromagnetic, and then we're going to talk about your transverse and your longitudinal again, but we're going to talk about it in terms of their properties. All right. Section 2 does not have as many notes, so that's good. So we're going to run through here real quick. So the first part that we're going to talk about is the amplitude for your waves. Okay, so amplitude is going to be how much energy these waves give off, and you can see based on your crest and troughs. Okay, so if my dotted line is my rest position, I would measure how high my trough is, and that would give me my amplitude, or I can measure how far my trough goes. Okay. So the higher the wave goes up, the more amplitude. The lower the wave goes down, the more amplitude. Okay. And amplitude is a fancy word for energy. So the higher your amplitude, the higher your energy. That, of course, is for a transverse wave. When we look at our longitudinal waves, we're going to do the same thing. We're just going to look at our compressions and rarefactions instead. Okay, so for a high energy wave that's longitudinal, you want your compressions to be real close together. And you want your rarefactions to be really spread out. All right. If you have a wave that doesn't have a lot of amplitude or doesn't have a lot of energy, your compressions aren't going to be close together and your rarefactions aren't going to be real spread apart. Okay, it's just going to be kind of mixed in together. Okay, so if you have a compression and it's real close together, that means it's high energy. If your rarefactions are real spread out, it's high energy. So it'd have a higher amplitude. Okay. Let's talk about wavelength. Wavelength is used to measure your frequency. So we need to know what an actual wavelength is. And that is just going to be how you break down your different waves. All right. So let's look at our transverse. For a transverse wave, you are going to look from crest to crest or from trough to trough. Okay. So you can't measure crest to trough, one trough to the next trough. And that's your wavelength. So we would measure how many of those pass by in a certain time point. Okay. So for your transverse wave, can you guess what we're going to measure here? We're going to measure from compression to compression or rarefaction to rarefaction. Okay. Same concept that we did with our crest to crest and trough to trough. You just measure what property that wave has. Okay. All right. So we know what a wavelength is. We know what the parts of our waves are. So let's talk about frequency. Like I said, frequency is how many of those wavelengths are going to pass by. It's how frequently you see those waves. Okay. Frequency is always going to be measured in hertz, H-E-R-T-Z. You may see it as 1 per second because that's what our unit of measurement is. But our main SI unit is going to be a hertz. Okay. All right. So frequency is how many of those wavelengths are going to pass by in a second, but we can also measure how fast the waves actually are. And that's going to be with your wave speed. Okay. So your different waves are going to travel at different speeds depending on what they're going through. Remember how we talked about mechanical waves can only travel through matter? Well, they're not traveling through matter at the same speed, okay? So mechanical waves are going to travel fastest through a solid, and it's going to travel slowest through a gas. All right. Has to deal with the particles in each of those. Remember how your solids, your particles are real close together and they just vibrate, and your gases are all spread apart. So your mechanical waves are going to travel faster when they have that close contact. Okay. Electromagnetic waves are kind of the opposite end of the spectrum. We said that it's the only wave that can travel through the vacuum in space. So that's actually what it's going to travel fastest through. Okay. So empty space will be the fastest for an electromagnetic wave. And then opposite of that, it's slowest through solids. Okay. You do have a formula for wave speed. All you have to do is plug it in, and it is frequency times wavelength. Okay. Frequency times wavelength. All right. Your book may show you your little symbol for frequency is F, and then lambda is the symbol for wavelength. Okay. We're going to measure that in meters per second. So you just plug it in and you're good to go. As far as notes go, that's it to section 2. Like I said, not a whole lot there. You're just recapping what you learned about each wave in section 1 and then applying it more concrete and with math as well. Okay. So section 3 is going to pick up a little bit more, talking about some more properties of waves, kind of their functions and what's happening in terms to us here on Earth. It's not difficult. You can handle it. But like I said, if you have questions, let me know. Feel free to email me if it's later in the day. Okay. As far as your quizzes go for this week, I don't want you to stress about them. They do have separate due dates. Okay. So if you wanted to go ahead and get them all done, that's fine. Or if you want to pay attention to the due dates and wait until then, that's cool too. Okay. The grading's a little bit different. You may see something on Google that's a little bit different from Renwell. That's because Google is on a point system right now. So it's going to measure your points instead of like your traditional 100 level. Okay. So let me know if you need me, and I'll see you next time. Bye.